Welcome back, geographers. In this video, I'm going to give you the foundation you'll need to start making sense of the data we'll be exploring this semester. Today, we're going to start with an overview of tables. In order to understand data, we really need to understand data tables like spreadsheets because we use a lot of tables in GIS. In a way, tables are kind of the foundation of data science, and we need a solid understanding before we can move on to other topics. You know from our practice exercises that we work not only with location data, but also other information that may be associated with locations, such as the number of people in a county, the length of a river, and the slope of a hill. So for today, we won't be focusing on location. We can think of data tables much like a spreadsheet. Data tables and spreadsheets are comprised of rows and columns. Columns are vertical and rows are horizontal. Columns are commonly referred to as fields in GIS. This can be thought of as all the values of a particular attribute. For example, these are all latitude values. The next column are all longitude values. Everything within a field is the same type of data, so all values within the latitude column only refer to latitude and nothing else. Don't worry about what the field or column names are for now. For example, latitude and longitude. We'll get into that in the future. Rows are commonly referred to as records. These are single observations, for example, an instance of an earthquake event. Each earthquake event has entries for the day and time when it occurred, the magnitude, the depth, and the location expressed in latitude and longitude. The values change from column to column for a single event to express different attributes, whereas in a column, everything is of the same type of data but represents each of the earthquake events that occurred. As a review, columns equal fields and rows equal records. Today, we'll see how we build these tables and best practices for their creation. A lot of GIS software is built upon older software such as Microsoft Access databases. This older software has some old and esoteric rules, so these conventions that you see on the slide are very important to note. If you don't follow these conventions for your GIS projects, you will likely run into many issues when you carry out your own GIS analyses and assignments. Keep field names short, no more than 10 characters. Don't include spaces, don't use special characters, and use underscores in place of spaces if needed. Having only 10 characters to work with makes meaningful column names challenging. As a result, you should always include a list of column names and their definitions with your data tables. Here's an example table I built from the USGS using their earthquake data. Notice how easy it is for humans to read and understand this table. The column headings are easy to understand. We know the source of the data and when it was downloaded. We even have a link to column heading definitions. Unfortunately, computers aren't human and this table can't be used in your GIS software as it currently exists. Specifically, your GIS software looks for column headings in the first row, but our first row is a title. Next, we can't have empty rows in our tables. Also, if you remove the first 3 rows but you don't remove the last 3 rows at the bottom, that will cause the table not to load properly too. Notice that the column headings have special characters and spaces in them. Next, let's look at how this table would be formatted to use in your GIS software. All we want is a very simple and plain table. No formatting for the field names, no special characters included, and no extra information at the top and bottom. We don't have any empty rows either. Next, we're going to explore CSV using software you already have on your computer. I'm going to demonstrate using a Windows PC in the software Notepad and Excel. You can use Google Sheets or Numbers instead of Excel. You can use any text editor instead of Notepad. Along with this video, I've included the CSV I'm going to use to demonstrate. Download that CSV to your local computer. First, I want you to right-click and open the CSV with a text editor. On a PC, I'm going to use Notepad. If you're on a Mac, you can use TextEdit. Let me explain the data structure we're looking at. The file type, called a CSV, stands for comma separated value. Within a CSV, individual data entries are separated with commas. Don't confuse CSV files with CVS pharmacies. CSVs are great because you don't need fancy or expensive software to open them or edit them. It's just a text file. The first row consists of the column headers, which are also separated by commas. Every row after the header row are individual observations or records of an earthquake event. Each value separated by a comma is a specific field or a column for that event. The order of the data values follow the order of the first row of field names. For example, the date time of when the earthquake took place, then the latitude and longitude values, and its magnitude and depth. Let's close the text editor and open the CSV in a spreadsheet program. I'm going to use Excel, but you can open this in Google Sheets or Numbers. If you open the file in Excel or Google Sheets or any other spreadsheet software, it automatically tries to recognize and identify the columns and rows. Essentially, it organizes your data in an easily viewable manner, but you no longer see the commas. Your spreadsheet software knows to hide those when it displays the data. You can edit all these data values in Notepad, in Excel, or in Google Sheets. Now that we have a basic understanding of how we build data tables and store data within rows and columns, we can actually talk more about the values we put into our tables. Luckily, most data values fall into only a few types. At a very high level, we can think of data as either being quantitative or qualitative. Qualitative data can be thought of as anything represented by text. You may also hear this data type referred to as categorical or nominal, as in categories or names. Examples of categorical data are land cover data broken into different types of vegetation like deciduous forest, coniferous forest, tundra, desert, subtropical rainforest, etc. Examples of nominal data are the names of all countries in the world, the name of every state in the United States, or the name of every county within a single state. A key to qualitative data is that there is no intrinsic ordering to the categories. For example, deciduous forest is not greater than or worse than a subtropical rainforest. Within our data tables, we usually represent qualitative data with words or codes that mean a word or category. Quantitative data, in comparison, can be considered as anything represented with numbers. When we work with numbers, those values have inherent ranking or ordering. 1 is less than 2, and 2 is less than 10. When we store quantitative data in a table, we specify the types of values that can go in a single column. Integers are whole values. They can't have a decimal. We often use integers to represent counts of things like the number of people in a county. If we need to store quantitative values with decimal points, then we use what are called floating point values. We often use floating points to record sensor data, like temperature or humidity, for fields that contain geographic values like area and square miles, or rates and percentages. In the GIS world, we can pick between two specific types of floating points. One is simply called float, and the other is called double. The only difference between them is the number of numbers past the decimal points that each point can support. Floats can have up to 7 values after the decimal point. Most of the time, this is more than enough. Doubles are more precise and can have up to 15 numbers past the decimal point. We primarily use doubles when we are specifying latitude and longitude. So why does knowing about the types of data we can put in our table even matter? Within your GIS data tables, you can only store one type of data in a single column, and you have to specify what that type is before you start. For instance, if you create an integer column of data in a GIS table, and it turns out some of your values actually have decimals, then you have to create a brand new column with a type of floating point. You can't simply change the field type, and your GIS won't let you add decimal points to integer columns. Let's take a minute to explore the earthquake data and see if we can separate the columns into qualitative and quantitative. Once we know which columns are quantitative, then we'll break those down into integer and floating point types. So once we have our data into a table, how do we know what the data means? One of the best places to start is with descriptive statistics, also sometimes called summary statistics. Don't panic, we're not talking about chi-square or ANOVA test here. Here's what we mean by descriptive statistics. Which county in Tennessee has the most opioid prescriptions per person? This would be the maximum value in our data column. Once we know which county that is, we can ask other questions like, why does that county have so many prescriptions per person? We can also ask policy-related questions like, should we do something about it? And if so, what should we do about it? We could also ask if that one county is way higher than the others or just a little bit higher. In that case, we are looking for outliers in our data. Here's another set of questions that utilize descriptive statistics. Which pharmacy in Knox County is dispensing the most opioids? Again, this is looking for the maximum value. Once we know which pharmacy that is, we can ask, how much more are they dispensing than the average pharmacy? To answer that question, we would want to know the mean, median, and standard deviation of our data. One last example. Which county in Tennessee has the lowest fatality rate from COVID-19? We would need the minimum value in our data table to answer this question. Once we know which county that is, we can ask public health questions like, why is the rate lower there? We can follow that up with policy questions like, is there something that county is doing that the rest of us can learn from? Let's take a look at some common types of descriptive statistics. For qualitative data, that is data represented by text, we can count how many times a particular word or category shows up in our data. We can also find which values in our data are unique, as in only occur once. There are a few more listed here. For quantitative data, we have a lot of options that you'll be familiar with from your math classes. We'll practice creating these simple statistics in several of our labs this semester. Again, don't panic. The software does all the calculations for us. It will be our responsibility to examine the results of these descriptive statistics to help better understand our data. There is one other way we can quickly explore our data that I want to share with you. Sometimes we just need to get the general trend of our data so we can see if there are any outliers, if most of the data values are clustered, if the data is evenly distributed, or if the data seems to be split. We use what is called a histogram to better understand this general trend in our data. The histogram looks just like a bar chart. We have an x-axis along the bottom that covers all the values in our data set. The y-axis along the side represents the number of times that data value appears in our table. The height of the bars tells us how many of that value there are in our data set. Let's use a simple example to demonstrate. Every week you sort your recycling into cardboard, plastic, and glass. This is an example of qualitative data because we sort the recycling into categories. If you count how many pieces of each type of recycling you have, we can plot the data in a histogram. This will quickly show trends in your recycling data. From here, we can start asking questions and making inferences from our data. For instance, maybe we have a lot of cardboard and we suspect that is due to a lot of online shopping. We can use the same technique to explore quantitative data too. In this hypothetical example, we have the heights of 50 students in a class rounded to the nearest inch. We sort the data from smallest to largest along a number line. Anytime a height appears more than once, we increase the height of that column. In this example, we can see that the data has a tall peak in the middle and trails off on either side. Other data sets may be clustered to one side or the other, while other data might even have two peaks. And some data may seem to be evenly distributed. Just like with our recycling data, once we see how the data is distributed, we can start to ask questions about why it's distributed that way. Our GIS software automatically generates histograms for our quantitative data, so we'll be exploring histograms for our data in our labs too. That's enough data science to get you started this semester. Now it's time to practice what you've learned.